Hey guys, welcome to the NCEA Level 3 Calculus Complex Numbers paper from 2022. If you're joining us for the first time, the way this video works is that I go through each question and let you guys know what you need to do for achieved merit and excellence. The best way to watch this video is to pause the video at the start of each question, have a go by yourself, and then unpause the video just to see how I go about answering the question. So yeah, without further ado, let's get started. Alright, so let's get started with question 1a here. Nice achieved question. So we've got 12k over 1 plus root 5. And what we need to do is we need to multiply by the conjugate of the denominator, which is going to be 1 minus root 5. And we've got 1 minus root 5 in the numerator as well. Then we've got to multiply the numerators. And then in the denominator, you've got difference of two squares. So it should be fairly kind of easy for the denominator. So you got 12k minus 12k root 5 divided by 1 times 1 is 1. The inside terms, forget about it, we don't really need it. And we've got minus root 5 times root 5. Well, that's just going to be positive 5. So let's just get rid of that. And we're going to put that as just 5. So then what we have is 12k minus 12k root 5 divided by negative 4. Separate the negative denominator, so you're going to get 12k divided by negative 4 minus 12k root 5 divided by negative 4. And of course, this could be written as negative 3k plus 3k root 5. So we can say that a is equal to negative 3 and b is equal to positive 3. Now you don't really need to do that. I mean, it doesn't really say show what a and b is, but it's just good habit to kind of get that kind of done. So correct solution is going to get you an achieved. Cool. We go to the next question. So with the next question, what we've got here is, I'm just going to keep my answer schedule here, but that's fine. Let's just do this here. So we've got u over v. So we're going to go u over v, which means we're going to get m to the power of 5 cis pi over 3 divided by m squared cis pi over 5. So in this case, we just got to get rid of the m. First off in the denominator, so you're going to have m3. And of course, this could be written as m cubed. Now the cis, what you could actually do is pi over 3 take away pi over 5. Now, okay, you've got to kind of simplify this. You can't really kind of leave it like this. So we're going to kind of do that real quickly. M cubed cis, I'm just going to kind of go pi over 3 minus pi over 5. I'm going to multiply by 5 for the denominator and numerator, multiply by 3 in the denominator and numerator. So what I've got here is m cubed. I got cis 5 pi over 15, take away 3 pi over 15, and of course this could be written as 2 pi over 15. Grades wise, this is going to be an achieved question. Now I'm looking at that second line, right? You can literally jump from the second line to the last line because I mean, and it doesn't matter whether you have a graphics calculator or a normal calculator. It's basically just using, just kind of saving a bit of time. So I just go 1/3 minus 1/5 because pi is a common factor, so I can take it out, which means I'm going to get 2 out of 15. I just go straight from like that second line to the fifth line in like one shot. Saves you a bit of time. I think that's the important part about this. All right, let's go to question C. We got u, v, w, find k if argument of u, v, w equals to pi over 4. Now, so they got 2 plus ki. Okay, so that's fine. I mean, I think we've got to do it one step at a time. So you've actually got to do u times v first. So I would actually put this as 3 plus 2i times 4 plus 2i. Expand the quadratic, so we're going to get 12 plus 6i plus 8i plus 4i squared. We're going to get 12 plus 14i. 4i squared, I squared is -1. So I'm just going to write that anyway, because I know people sometimes go, whoa, where did that -1 come from? So remember that I squared is equal to -1. And because I squared equals to that, we're going to get 12 plus 14i minus 4. We're going to get 8 plus 14i. So next we've got to actually work out UVW. So we're going to go UV times W, because that's going to give us the UVW there. So I've got 8 plus 14i multiplied by 2 plus ki. All right, so the next thing is kind of go carry on here. So I've got 16 plus 8 ki plus 28i plus 14 ki squared. Putting this all together, I'm going to get 16 plus 8 ki plus 28i plus 14k times -1. Not a fan of this purple colored pen, but it's alright. 16 plus 8ki plus 28i minus 14k. Now this is what UVW equals to. So I'm going to put down UVW is 16 minus 14k plus 8ki plus 28ki. Now we got to try and figure out the value of k, but the big clue right now is this right here. All right, remember that pi over 4 is 45 degrees. All right, if it's 45 degrees, then we're working with an isosceles triangle. And if we're working with an isosceles triangle, then we know that the real part equals to imaginary. So these are some of the things that's actually worth remembering. Every time you see this pi over 4, you got to kind of register in your head straight away that you can kind of say, since argument equals pi over 4, we can actually say that real equals imaginary. All right. So if you look at the real part is 16 minus 14k. So that's the real part. And if you look at the imaginary part is actually 8k and 28k. Now, did I miss? No, that's not 28k. I thought I copied it wrong. Oops. That should be 28i. Let's fix that up, shall we? There we go. 8k and 28. So if that's the case, I could actually put this as real. Real is 16 minus 14k equals 8k plus 28, because this is now saying that the real part is actually equal to the imaginary part, and that's because of the 45 degrees, right? So next part is I'm going to bring all the k's to one side. So I've got negative 8k minus 14k equals 28. I'm going to take the 16 to the other side. I've got minus 16. Then what I've got here is negative 22k equals 12, and then k is equal to 12 divided by negative 22. Now, of course, you could actually simplify this and rewrite this as negative 6 over 11. Now, grades wise, the correct solution is going to get you a merit here. As for achieved, you've got to get up to 16, I'd almost say getting up to here, or even up to here. You'll be looking at an achieved for this particular question. Cool, so let's go on to the next one. My favorite. Find the values of p. There's only one real solution. Okay, so the first thing to kind of notice is that we have got only one real solution. That straight away is telling you that we're thinking about discriminant, and b squared minus 4ac equals to 0. Now that's the first part that you kind of have to go. When you see that one real solution, we're going to put that as b squared minus 4ac equals to 0. The problem is we don't have a quadratic equation. What we do have is like a weird looking equation, right, over the square root symbol. So we got to rearrange first to get rid of the square root symbol. Once we get rid of the square root symbol, then we should be able to bring it into a quadratic formula, and then we should be able to find out the values of p. So we've got x minus 2 root x plus p equals minus 5. Now what I'm going to do is I'm going to take this entire thing to the other right hand side, and I'm going to bring the minus 5 to the left hand side, which means that it will become x plus 5 equals 2 root x plus p. Now once that's done, what I'm going to do is I'm actually going to square both sides. So I'm going to square this, and I'm also going to square this side as well. Now x plus 5 squared, that's just what do we got? X squared plus 10x plus 25 equals, now in this side you got to be careful. All right, so first you got to go 2 squared. 2 squared is 4, and then square root of x plus p, the square root actually disappears, which means you're left with just 4x plus p. Next step is we need to expand our brackets here. So we've got x squared plus 10x plus 25 equals 4x plus 4p. So rearrange this now. So we're going to get x squared plus 10x. We've got minus 4x plus 25 and minus 4p. And all of this is equal to 0. So once that's done, we can simplify this further to x squared plus 6x plus 25 minus 4p equals to 0. So now we have our quadratic formula. We can actually chuck it into the discriminant formula to try and figure out what p has to be. So we've actually got a is equal to 1, b is equal to 6, and c equals to 25 minus 4p. So just kind of reiterating that, we've got b equals to 6 from there, we've got c equals to 25 minus 4p from there, and then finally a is equal to 1, which is just the coefficient of x squared. So with that in mind, we're going to put down b squared minus 4ac is equal to 0. And we've got 6 squared minus 4 times 1, ignore that, so 25 minus 4p equals to 0. So kind of expanding this out now, we've got 36 minus 4 times 25 is 100, plus 16p is equal to 0. So we've got negative 64 plus 16p is equal to 0, and 16p is equal to positive 64, which means we can actually work out what p is, which is 64 divided by 16, so p is equal to 4. So grades wise, guys, we're looking at p equals to 4 as a merit. Correct quadratic is actually getting you an achieved, so it's actually up to here. You're actually getting an achieved for this question. All right, so let's go to the next question here. All right, guys, so we've got a lovely proof question here. Modulus w plus z. Okay, so what we're going to do is we're going to have to make up two complex numbers first. So we're going to write down w equals to a plus bi, and we're going to write down z is equal to c plus di. Now with that in mind, I'm just going to kind of point out something here. One of the things to look at here is that they actually say this proof, whatever this left hand side is, on the right hand side we're looking for the real part of w and the real part of z. Now if you look at the real part of w, that's actually a, and the real part of z is actually c. So what we are trying to do is we are trying to take this entire equation and we're going to have to kind of prove it that it equals to 4ac. Okay, so that's kind of like the first thing that you kind of need to recognize here. Now it's just a matter of like substituting all of that in. So I'm going to go with w plus z first, right? So when we do w plus z, we are going to get a plus bi plus c plus di. So my real parts of that is going to be a plus c plus bi plus di. And I can rewrite this as a plus c plus b plus d, and I'm going to put that I in there. Now, it's actually asking for the modulus squared. So if you think about it like this, like when you're trying to find modulus, you're going to get square root of square root anyway, right? But we're squaring that, so that means that square root almost becomes null and void. So if you think about it, it's like normally when we do like, I don't know, if you have like 3 plus 4i, and if you want to find the modulus of this, you'd go, well, if modulus of 3 plus 4i would be square root of 3 squared plus 4 squared. But because they actually put the square on top here, you're actually squaring this, and so you don't really need to worry about the square root at all. So based on that idea, what we can kind of do here is we could actually say that when we have w plus z squared, I'm actually going to do this the long way first so you can kind of see what's happening. The w plus z, so that means it's going to be square root of w plus z's real value, which is a plus c squared, plus b plus d squared. And of course, this entire thing is getting squared. And remember that this squared is actually right from here. This is what's happening right here. And because it's squared, I can almost forget about the square root symbol, because the square root symbol and squared cancel out each other. So I've actually got a plus c squared plus b plus d squared. Now this thing right here is, I'm going to need a different kind of color, but like it's fine. I'm going to try and do this. So this entire thing is this part here. All right, now I need to work out the w minus conjugate of z. So the first thing I need to do is like, I'm going to work out conjugate of z. It's going to be c minus di. So on this side, I'm going to go w minus z. So I've got a, oh, that's actually z, conjugate of that. So I've actually got a plus bi minus, and in brackets, I'm going to have c minus di, which means I've got a plus bi minus c plus di. And I could rewrite this as a minus c plus b plus d. Actually, let's just do this one more step first. Di like this, a minus c plus b plus di. All right, and now if I look at the modulus of this, so w minus z modulus, and I'm going to do the same thing again. It's going to be square root of, and the square is going to be around the top. Now the real part of this is going to be a minus c plus b plus d squared. And what's going to happen is the square root and the square disappears, and we're left with just a minus c squared plus b plus d squared. Okay, now if you look at the original proof itself, right, it actually, the original question in the pink box, let me show you guys. Is this going to work? Yes, it is, because this is the part I've actually figured out right now, the red part there. It actually says it's minus, so I'm taking the orange minus the red, and this is of course going to be around in a bracket. So what I've got here is a plus c squared. I'm not expanding anything yet. B plus d squared minus, you can put this as a minus c squared minus b plus d squared. And basically what happens here is these two things get cancelled out. And because they cancel out each other, what we're left over with is just a plus c squared minus a minus c squared. And what we ended up with here is we've actually got a couple of quadratic equations that we've got to expand. And I'm going to try and kind of do it here. So I've got a plus c times a plus c minus a minus c times a minus c. So I've got a squared plus 2ac plus c squared minus a squared minus 2ac plus c squared. Now taking that taking everything out of the bracket, I'm going to get plus 2ac plus c squared minus a squared plus 2ac minus c squared. And straight away you guys can see that the a squareds disappeared, the c squareds disappeared, and you're left with just 4ac. And remember that the a is the real part of w, so we could actually rewrite this as real part of w, and the c is the real part of z, so we could actually write this as real part of z. And basically we've done the proof right there. So the correct solution for this proof, guys, is getting to the final step is going to get you an excellence grade. Correct expanded form for that is going to get you a merit. So I'm assuming that this line here is going to get you a merit. Now, unfortunately, I can't see any on the marking schedule. Let's have a look. Yeah, there's nothing. There's nothing there for achievement, unfortunately. Sorry, but yeah. So this question is like straight up. Either it's a. And as for the, we're looking at the grades for this question. You do get an E8 with just that excellence straight away there. If you get an excellence, if you make a minor mistake, you could still get an E7, which is actually fairly kind of kind there. All right, so that's basically question 1 for us. Let's go to question 2. All right, guys, so with question 2, what we've got here is dividing this gives us a remainder of value of b. So basically what it's saying is that if we put f of -2, then we should get it as 3 for this equation. So we can actually write down 3 equals -2 cubed minus 3 times -2 squared plus b times -2 plus 9. So we've got 3 equals -8. We've got -3 and 4, which is -12, minus 2b plus 9. So 3 is equal to -20 and 9, oh god, -11 minus 2b, and we've got 3 plus 11 equals -2b, so 14 equals -2b, and we can say that b is equal to 14 divided by -2, therefore b is equal to -7. Grades wise, this is just a straightforward achieved question. Yeah, so if you get like one of these remainder questions, just remember you take if you're wondering how I got that -2, it's just x plus 2 equals to 0, and you get x equals to -2. You substitute that -2 in the equation, and that's how you do it. Sometimes they ask you the question of like, what is the remainder? So in that case, all you do is you just put reverse the factor, put it equal to 0, get a solution, and then substitute in the equation to get the remainder. It's one of these standard questions that just keeps coming. Right, next one, we've got find the complex number for which blah 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 is 15 minus 2i. So we're going to put down z equals a plus bi, which means conjugate of that is going to be a minus bi. So what we've got here is a plus bi plus 4 times a minus bi equals 15 plus 12i. So we've got a plus bi plus 4a minus 4bi equals 15 plus 12i. We combine all the a's together, we get 5a minus 3bi equals 15 plus 12i. So what we're going to do, match the real, match the imaginary to imaginary. So basically that means we've got 5a equals to 15, a is equal to 3, we've got -3b equals to 12, so b is equal to -4. Now it is important that we kind of need to put this together. It does say find the complex number z, and because we said z is equal to a plus bi, we do need to finish it by saying that it's 3 minus 4i. Grades wise and achieved for this question. And let's move on to the next one. So looking at this question, you know, they've slightly changed this from the previous years. I know in the previous years they actually give you the complex number and then you can find the conjugate and then work out the real, but this time they've done it slightly different. And unfortunately with this one you've got to actually do it using long division. And yeah, it's I mean, if you know how to do synthetic, you could always go with that as well. But unfortunately this is the method that I kind of use, I've been using for a long time. If you have a different way of finding this, then go for it. But anyway, we're gonna get started with this. Now it says that z equals to minus 4, which means z plus 4 is a factor. So with that in mind, I'm going to use long division here. So I've got z plus 4 and I've got z cubed minus 2z squared plus hz plus 180. Now remember that z plus 4 is a factor, and because z plus 4 is a factor, that means you know, the remainder has to be 0. If that's the case, I'm wondering, do we need to use long division? Well, you know, if you think about that original question, like, I'm going to try and do this without the long division. I mean, I know we could do this to long division, but I'm going to try and do it without long division. If z minus 4 is a factor, then the remainder is 0. That means I could actually put in the original equation negative 4 cubed minus 2 times negative 4 squared plus h times negative 4 plus 180. All of that should equal to 0, theoretically. Now looking at the answer schedule, h is supposed to be 21. Let's try and see if this actually works out to be 21. Negative 4 cubed is negative 64. We've got 16 times that is going to be negative 32. Negative 4h plus 180. All of that is equal to 0. So I hope this is going to work out. You know, it's one of those things where you go, I think it's going to work out, and then you go, oh, maybe not. 90, oh, not 93, 96 minus another 3, 84. This is looking sketchy, guys, but let's see. 84, actually maybe not. Plus 84 equals to 0, so negative 4h equals negative 84, and h equals negative 84 divided by negative 4, which means h equals to 21. Well, lo and behold, I do have 21. But that doesn't help me with anything, because while doing it this way, I've got h. I've got h, but I still need to get that, what do you call it, the other factor. Now here's the thing, I am not sure, but like, no, actually no, I am sure, because I'm just looking at the answer schedule. They actually say that other solutions found algebraically. It kind of sucks, right? Because the thing is, it's like, I know I can put this in the graphics calculator and get the results, but looks like there is no other way than doing by long division. So I've just wasted some time of ours. Sorry about that, guys. But let's go back to long division then. Okay, so I'll try my best to kind of do it with a color combination so that you guys can see what's happening where, all right? So the first thing is I want to get rid of z cubed, so I'm going to have to multiply everything by z squared, which means I'm going to get z cubed minus 4z squared. When I do this, I am going to get z cubed minus z cubed is 0. So that's 0. Then I've got negative 2 minus minus 4 is going to make it 2z squared. Bring down the hz. Just realized I made a mistake. That should be plus 4. Talk about rookie mistakes here, mate. So it's going to be minus 6z squared. Alright, so with that in mind, Next thing is I need to get rid of minus 6. So I'm going to write that as minus 6z, which means minus 6z times z is minus 6z squared, and then times it by 4. I'm going to get minus 24z. Okay, so that means in the next line I'm going to get 6x squared, 6x squared disappears, h minus minus 24 will become h plus 24z, and then the 180 comes down and I've got plus 180. So what do I multiply by? Well, I know that I've got to get rid of the number 180, right? And the only way I can get rid of 180 is by multiplying by 45. And so what would happen is I'd get 45z plus 180. And remember that the denominator here, the remainder has to equal 0. If that's the case, then h plus 24z minus 45z should equal to 0. Expand it out, I'm going to get, what am I going to get? I'm going to get h plus 24 minus 45 is equal to 0. So h minus 21 is equal to 0. And I get h is equal to 21. All right, but the thing is, I do need to find the value of h, which I've shown two ways of finding the value of h. But the other solutions, I'm actually looking at the factor here, which is z squared minus 6z plus 45. So I need to factorize that. Z squared minus 6z plus 45 is equal to 0. Now you could put this in the, what do we call it, quadratic formula, but you'd have to do it manually because they want the answers shown algebraically. But what we could also do is complete the square. So I've got z squared minus 6z equals negative 45. With that in case, I could complete the square by going z squared minus 6z. Now half of negative 6 is negative 3. Negative 3 squared is actually, negative 3 squared is 9. So I can go plus 9 on both sides. And when I do this, I actually end up with z minus 3 squared equals negative 36. And because negative 36 could be written as z minus 3 squared equals 36i squared, because remember negative 1 is just I squared. Carrying on, I've got z minus 3 equals to square root of 36i squared. So z minus 3 equals plus or minus 6i, and z is equal to 3 plus or minus 6i. So if you look at it, find the other solutions in the form a plus bi. We've done that, and we've done value of h as well. So for grades wise, you've got to get z in this format and h. For achieved is getting 1 of z, it's a or. For merit, you've got to get both. Cool. Bit of an annoying question. Like, I don't think I've seen a question like that pop up at all. I don't think I've ever seen one like this in the last few years that I've done calculus papers anyway. Good question though, very good question. All right, let's go to the next one, question D. So with question D, we've got z equals that, w, find argument. Okay, fine. So we're gonna work out what w is first, right? So w is equal to 4 over 1 minus square root of 3i minus 2. We're just going to kind of put that separately there. We've got to multiply by the conjugate of the denominator, which is 1 plus square root of 3i, 1 plus square root of 3i, and of course we've still got the minus 2 kind of hanging around there. So next step is we've got to multiply, and we've got difference of 2 squares in the bottom denominator. So we've got 4 plus 4 root 3i divided by 1. The inside terms don't really matter. We've got minus 3i squared minus 2. Then we've got 4 plus 4 root 3i divided by 1 minus 3 negative 1. Carrying on here, we've got 4 plus 4 root 3i divided by, that becomes positive 3. 1 plus 3 is 4 minus 2. So we've got 4 divided by 4 plus 4 divided by 4 root 3i minus 2. We've got 1 plus root 3i minus 2, and we can get negative 1 plus root 3i. All right, now this is what w is, and we actually need to figure out what the argument is. Now, if you guys remember, like, and if you have been watching some of my old videos from, wow, I'm gonna hit about 9 years ago. Wow, that's a long time. Long time indeed. 2013, 7. No, it's 10 years ago. Wow, that is 10 years ago. Jeez. Anyway, let's kind of look at this. Negative 1 is here. Positive root 3 is somewhere here. So our complex number is there. So we've got to actually work out what this angle here is. So we already know it's going to be 90 plus whatever this little angle is. Now, here's where special triangles come into play. Now, looking at this, this is 1 and root 3. You should straight away recognize that we're dealing with special triangles. So if you have a look at this, we've got 1 and root 3. And so we're dealing with this the 30 degree / 60 degree triangle there. All right, so we just got to try and match up which part of where everything is, and then we should be able to kind of get it. So we're going to actually try to kind of rotate this triangle here, but give me a second. Where is this? All right, so what I've got here is I've got the special triangle there, and I'm just going to flip it upside down here, because the square root of 3 is this part right here. That's the square root of 3, and then you've got the 1 right there, which is going to be at the top, which means this little angle here is going to be 30. So I'm talking about this angle here is going to be 30 degrees. So we can kind of say that the argument of w is 90 plus that 30, which equals to 120 degrees. Grades wise, this question is worth a merit for this. Correct expression for w with rationalized denominator is worth an achieved. That means we're looking at somewhere here for an achieved. All right, guys, let's go to the final question. Well, final question in this question. So we've got a locus question, and we need to write it in a circle form. All right, so locus questions, all you got to do is put down z equals, I don't know, x plus iy, and then just manipulate the whole way through, and eventually you're going to come up with this thing right here. So I'm going to put down z equals x plus iy. So modulus of z plus I, we've got x plus iy plus I equals to 2 z again, so x plus iy minus 5i. All right, so collect all the real parts first, which is going to be x. The imaginary parts, which is going to be y plus 1i, equals 2 times. The real is x. The imaginary is going to be y minus 5i. And that's what we're left with here. So if you remember a few questions back, we did this. When you have a modulus, you're just going to take the square root of the real, in this case, which is x squared, plus the imaginary, which is y plus 1 squared, equals 2 times square root x squared plus y minus 5 squared. Now get rid of the square root symbols. You've got x squared plus y plus 1 squared is equal to, now 2 squared, this is where people forget about it. The 2 gets squared, which means you're going to end up with 4 times x squared plus y minus 5 squared. Now expand the brackets. Now, unfortunately, it's not just expanding the brackets. You got to expand this quadratic, right? So you got y plus 1, which means you're going to get y squared plus 2y plus 1 equals 4 times x squared plus y squared minus 10y plus 25. And expand the bracket. We've got x squared plus y squared plus 2y plus 1 equals 4x squared plus 4y squared minus 40y plus 100. All right, so we got a ugly looking equation, but let's just make the left hand side 0, which means I've got minus x squared minus y squared minus 2y minus 1. So I'm going to end up with 3x squared plus 3y squared minus 42y plus 99. All right, so now I got to come up with the equation of this in the form of that form that they've given, right? The circle equation. Now, what you can do is, you got to complete the square in this, right? It's not too bad. I mean, like, you've got 3 as a common factor, so you can actually take out 3 as a common factor and get rid of it. So you're going to get 0 is equal to x squared plus y squared. Now 42 divided by 3 is minus 14y, and 99 divided by 3 is 33. Now, what I am going to show you guys is this. If for some reason you don't have a calculator and you're attending calculus, man, that's epic, it's super awesome. But if you do have it, go down to this section here in conics, and I believe we found this out last year. It is this right here, this particular equation in conics. You can just press enter and you can put the coefficients of these things. So right now, if you look at it, x squared, our coefficient of x squared is a, but in our equation it's actually 1. Y squared is also 1. We don't have any x, so we're going to leave that as 0. And do we have a c? Oh no, wait, we don't have a bx, do we? No, b is 0. Bx, that's right, sorry, oops, I made a mistake there. B is actually equal to 0 because b of x, we don't actually have x at all. We do have y, which is equal to negative 14. So I'm going to put that down as negative 14. And then we've got d, which happens to be 33. All right, now what this does is this actually draws the circle for us. So when we draw it, obviously it's up there somewhere, but we can click on G-solve and we look at the center right there. If you look at the center is at 0, 7, and the radius is actually 4. Now the center is 0, 7. We know that this is going to be x squared plus y minus 7 squared equals radius squared, which happens to be 4 squared. So you've got your answer straight away there from the calculator. All right. Now, for some odd reason, you kind of don't have a graphics calculator and you're like, how am I supposed to do this without a graphics calculator? Well, that's where completing the square comes back again. So we're going to rewrite this as x squared plus y squared minus 14y equals, it was 33, positive 33. I'm going to switch it to the other side. Well, let's actually do this step one more time. Just so that all I've done is I've just switched the sides, guys. And then I'm going to rewrite this as negative 33. And x squared, I don't really need to touch it, but I do need to touch the y squared. Because half of negative 14 is negative 7, and negative 7 squared is positive 49. So I'm going to go 49 on both sides. And what I end up with is x squared plus y minus 7 squared equals 16. Now they do say the answer has to be in k squared, so I'd actually put this as x squared plus y minus 7 squared equals 4 squared. And as you guys can see, that is pretty much what I got in the top there in the light blue, which there's nothing wrong in doing that. So grades wise, final correct solution gets you an excellence. Correct expanded quadratic. Expanded, but it doesn't say simplified. So I'm not sure. I'm not sure whether you'd get an achieved in this line here or whether you'd get an achieved in this line. So I'm not sure. It could be either one of those two lines there. Sorry, that's not an achieved, that's a merit. My bad. Okay, so going to the answers, and once again having a look at those. If you get the excellence question correct, fully correct, you get 8 points. Minor error, you're looking at 7, but I'm guessing minor error could be like something like, you know, not doing this last line properly or whatnot. So yeah, so that's basically question 2. We go to question 3. Alright guys, let's go to question 3 here. What do we got? We got V equals 2R minus S. So first thing is I've got to get down what R is. R is 3 plus 2I. And S is 2 minus 5I. And V is equal to 2R minus S. So I've got 2 times 3 plus 2I minus S, which is 2 minus 5I. Now be very careful about this minus here, because people forget that minus 2 minus 5I, they forget to put that in the bracket, and they forget about this negative, and negative make a positive there. Alright, other than that, we've got 6 plus 4I minus 2 plus 5I. This actually gives us 4 plus 9I. And we've got to plot it correctly. So 4 plus 9I is somewhere here, and we're going to put that as V. That's going to get us an achieved grade right there. All right, part 2 of this second B. Question B is we've got equation, give you a solution in AK plus BKI. So a couple of ways you could do this. You could actually use the quadratic formula where you put A equals to 1, B equals to 6K, and C equals to 15K squared, and kind of work it out. That's one way of doing it. Yeah, or you could do complete the square as well. Now let's actually do if you want to know how to do the complete the square, it is in the answer schedule. They kind of have done it quickly there. But what I'm going to do is I'm actually going to use the long method, which is the quadratic formula. So I'm going to go down A is equal to 1, B is equal to 6K, Z is equal to plus 15K squared. So then the solutions is going to be X equals to minus B plus or minus B squared minus 4AC over 2A. So minus B is negative 6K plus or minus B squared is 6K squared minus 4 times 1 times C, which is 15K squared, and all of that is divided by 2. So I've got negative 6K plus or minus square root of 36K squared minus 15 times 4 is 60K squared. And all of that is divided by 2. So I've got negative 6K plus or minus square root of 24K squared over 2. Unfortunately, I want to do square root of 24. I can't do square root of 24, but I can do 24 as 6 times 4. I'm going to take out the k squared first. So I'm going to get negative 6k plus or minus. Square root of k squared is just k. Square root of 24 over 2. And then negative 6k plus or minus k. 24 could be written as 4 times 6 over 2. So negative 6k plus or minus k. Square root of 4 is just 2. And I'm going to have square root of 6 left as it is. And I could rewrite this as negative 6k over 2 plus or minus 2k over 2 square root of 6, which means I get negative 3k plus or minus k root 6. Now, of course, I just realized I made a huge mistake, which is the minus right there. That should be a minus 24. So if that's 24 and minus, that's going to be 24 times negative 1 times negative 1 could be written as I squared. Of course, I squared when I Sorry guys, that's a huge mistake there. Yeah, the I should have been in there the whole time. Ki square root of 6. Apologies about that. It's just a bit late in the night, just trying to work this through. Unfortunately, this question is still only worth and achieved. That's a hell of a lot of work for achieved. I actually think completing the square might be actually a lot easier in this than to try and do this this long way. In kind of saying that, what do we got? We are going to go to the next question. These have to be one of my favorite types of questions, right? Complex roots. So the first thing we're going to go is we're going to rewrite this as z cubed equals negative, well actually no, we're going to put down the 0 in there. 0 minus k to the power of 6i. Right, that's our first step. Our second step is to actually write this in polar form. Now, looking at where this particular complex number is, we know that negative 6k to the power of 6 is somewhere here. So that's what we've actually got as our complex number. The modulus is going to be k to the power of 6, and the argument could be written as 270 degrees. Now, people always ask me, is it better to do it in radians or is it better to do it in degrees? Now, I would say do it in degrees because then it's easy to kind of like do the little cheat shortcut that I teach people, which is nothing wrong with it. It still works. But anyway, what we have here is we've got z cubed is equal to k cubed, k to the power of 6 cis 270 degrees, which means z1 is actually equal to k to the power of 6 cis 270 to the power of 1/3. We're going to get k squared cis 270 divided by 3 is actually 90 degrees. All right, so this becomes one of our first answers. Now, if you've been watching my complex roots videos, I've taught like a lot of shortcuts, and the shortcut in this case is that your complex number, it's a z cubed, which means you're actually going to have 3 answers, and all it means is that you find your first z1 and you just keep adding 122 times to it. So which means z2 will become k squared cis 90 plus 120 is 210 degrees, and then z3 is just k squared cis 330, because 210 plus 120 is 330. And that's pretty much it, guys. Like, you can actually just leave your answer in degrees, and I know that in the answer schedule they always love to give the answers in radians, but you know, when you look at the question, it doesn't really say state it in degrees or radians. Go with degrees, it's easier. Why waste time? So 3 solutions gets you a merit for getting all 3 solutions. Achieved will be just 1 solution there. All right, so question D. What we've got here is we've actually got to prove that there's no complex number z such that modulus of z minus z equals negative I. So guys, anytime you get a proof question, especially with these types of questions, you always put down z as a plus bi or x plus iy. It doesn't matter which one you use. You're just going to try and kind of work it out. Now, modulus of z is equal to square root of the real part plus the imaginary part. So let's write this as an equation now. It says modulus of z minus z is equal to I. So we got to prove that this doesn't exist. So modulus of z is square root of a squared plus b squared minus a plus bi equals to I. So we've got square root of a squared plus b squared minus a minus bi equals to I. Now remember, on the right hand side we've got only I, so we could actually write this as 0 plus I. And the reason why we're doing this is because if you'll have a look at these, all of these parts is actually the real part, and all of this is actually the imaginary part. So if we actually put down negative bi equals to I, we can actually say that negative b is equal to I divided by I. Negative b is equal to 1, so b is equal to negative 1. Now this actually works for b. But the problem is, let's have a look at what happens when we do the real parts. With the real parts, I'm going to do it here. Square root of a squared plus b squared minus a is equal to 0. I'm going to take the a to the other side and make it positive. Then I'm going to get rid of the square root symbol by squaring both sides. And when I do that, I end up with a squared plus b squared is equal to a squared. Now, problem is we've got b is equal to negative 1. So remember, we actually figured out that b is equal to negative 1. So we can actually write this as a squared plus negative 1 squared equals a squared. And what we're ending up with here is that a squared plus 1 equals a squared. Now, that's not possible. You can't get 1 is equal to 0. It's actually not possible. And this is pretty much how you actually prove that there is actually no complex number. So for this one, correct solution is going to get you a merit. Finding that b is equal to negative 1 is actually going to get you an achieved for this particular question. All right, so let's go to the last question. Here we go, another substitution complex numbers. All right, z equals to this. We've got I over z, and 3 over conjugate of z equals to 1. So basically, guys, the first step you've got to do is you've got to try and substitute z in on that left hand side and kind of bring it in together as one fraction. All right, so we've got z is equal to a plus bi. We've got conjugate of z is going to be a minus bi. So what we've got here is I divided by a plus bi plus 3 divided by a minus bi equals to 1. All right, now unfortunately there's nothing we can do here apart from cross multiplying here. All right, so what we're going to do is we've got I multiplied by a minus bi plus 3 times a plus bi, and the whole thing is divided by a plus bi times a minus bi, and all of that is equal to 1. Next, we've got to expand the brackets in the numerator. So we've got this and this. All right, so we've got a whole lot of expanding to do, which means we're going to get ai minus bi squared plus 3a plus 3bi, and all of that is a plus bi times a minus bi equals to 1. Now I squared is equal to negative 1, and so negative 1 times negative b is going to be positive b. So I'm going to write down all the real values first, right? So I've got 3a plus b plus ai plus 3bi, and the whole thing is over a plus bi a minus bi equals to 1. Once that's done, like I said before, I've got 1 on the right hand side, so I could actually write this as 1 plus 0i. What I'm going to do is I'm going to separate this big fraction on the left hand side with real part and imaginary part. So I'm going to write it down as 3a plus b, which is the real part, and I've got a plus bi times a minus bi plus a plus 3b bracket I, and I've got a plus bi and a minus bi. All of that is equal to 1 plus 0i. So at this point, what I can see is that this is the real part, which equals to 1, and this is the imaginary part, which equals to 0. All right, so I've actually got kind of like 2 sets of equations here, right? So my first equation is I've got 3a plus b is equal to 1. And what else do I have? Now I can't actually do 3a plus b equals to 1 because that entire thing is going to equal 1. Because there is actually a denominator there, and that denominator is going to be a pain. Now with the imaginary one, it kind of makes sense, right? Because for only the numerator has to be 0. We don't really care about the denominator for the imaginary part. So I guess we can't really say that 3a plus b equals to 1, but rather we have to say 3a plus b divided by a plus bi, a minus bi is equal to 1. That whole thing has to equal to 1 because the denominator has got, yeah, we don't know what that is. As for the imaginary part, we've got a plus 3b is equal to 0. So we can actually say that a is equal to minus 3b. All right, so that much we've got. A is equal to minus 3b. Now, going back to the real side, I've got 3a plus b divided by, I'm going to do difference of squares, which means I'm going to get a squared minus plus b squared equals to 1. Then cross multiply, I've got 3a plus b equals a squared plus b squared. And because I actually did solve this before, I said that a is equal to 3b, I could actually put in 3b wherever, negative 3b in there. So I'm actually going to get 3 times negative 3b plus b equals negative 3b squared plus b squared. So I've got negative 9b plus b equals 9b squared plus b squared. So I've got 10b squared minus 8b. So minus 8b equals 10b squared. Now I got to treat this as a quadratic. I can't just get rid of them straight away. So I'm going to put this 0 equals 10b squared plus 8b. 0 is equal to 2b is a common factor, which means I've got 5b plus 4. And what this gives me is 2b equals to 0, or 5b plus 4 equals to 0. So I've got b is equal to 0, or b is equal to negative 4 over 5. Now the problem is, if b equals to 0, a is equal to 0, and the whole kind of equation just kind of becomes it becomes void, right? So we're going to put down b is not equal to 0, because if b, we're just going to write that down. If b is equal to 0, then a equals to 0, and you know, we just say it's not possible, right? Like it doesn't work out. You can't have like 0 equals to 1. So actually we can't even do that because you can't divide by 0, so it just doesn't work out. So therefore we're going to put down b is equal to negative 4 over 5, and if b is equal to negative 4 over 5, then a is equal to negative 3b, which means we've got negative 3 times negative 4 over 5, which actually gives us 12 over 5. We figure out what z is then. Z is equal to 12 over 5 minus 4 over 5 I. So grades wise, we are looking at an excellence for this part. A equals to minus 3b is going to get you a merit. So right there, a equals to minus 3b, that part there is going to get you a merit. Now unfortunately, you know, there's again no achieved kind of parts for this question, and again with the grades, 8 points for the full solution. Minor error, you get like 7 points, which is an overall 21 gets you an excellence. So 3 E7s, even with minor errors, 3 minor errors, you could actually get an excellence for this paper. So yeah, so it's pretty much it for question 3, guys. Yeah, overall, I mean, I thought this paper was pretty good. I mean, it's, you know, some of the questions was like a bit tricky, like a couple of the merit questions. But the excellence ones was like quite nice. I mean, it's just straightforward proof questions, which is always nice to actually kind of do. Yeah, so my kind of like my tips for this exam, like I always say this to people with complex numbers, especially the like if you see like the locus questions or like the proof questions, just put down, you know, z equals a plus bi or x plus iy, and just start working through it. And most of the time, you know, you could easily get to a merit level in it if you just keep chipping away. Watch the previous exams. Like, you know, there's a lot of tips in the previous exams, and there's only a finite amount of questions that these guys could actually ask for complex numbers. And I hope, for the love of God, they'll never bring an investigation in like they do in level 2 or level 1. But apart from that, yeah, pretty straightforward paper. It was actually nice to do. Hey guys, that is basically it for this video. As always, don't forget to like this video, share this video, and of course subscribe to keep up with the latest content. There should be some playlists popping up. Check them out. Great revision material. And as always, thank you for watching.